yeah, good morning to you guys at the States. It's good evening for me over here in Israel. And welcome to my talk about auditing data and answering the lifelong question, is it the end of the day yet? Diana, you have a battery issue with your Mac. But anyway, if you're not familiar with that question, that's totally fine. We're gonna go deep into that question during the following hour. Next slide. So my next slide is the agenda slide. So what are we going to cover up today? So first, we're going to start from Nielsen's architecture. And we'll see that it really had little fires everywhere regarding data visibility. And we'll delve into that question that I've just mentioned, the end of the day question. After that, we're going to designing our auditing metadata. How we did it, the entire process behind it, and we'll see how that auditing data looks like. After we're done with that, we're going to talk about how we store the data, how we queried it to optimum. We're going to go into that question again, and finally how we answered it. And then last but not least, we're going to do some alerts and add-ons, which are always fun. Next slide. So the next slide is the most important slide of the presentation. It's just who I am. So who I am. I'm Simona. I've been dealing with data for the past 10 years now, which feels like a lot. I really like music. I really like Japan. I worked at Nielsen up until a few months ago. So this is totally based on a true story. And this is me. Next slide. So first thing we'll do is actually just delve into Nielsen's architecture. So what you see before you, and if I could, I would totally use my mouse to just emphasize what you actually see. But I'll just try with hand gestures. So what we see is how we collect data. So we collect data from various devices, right? From computers, from TVs, smartphones, etc. And then that data goes into our front-end layer. It gets collected into our data serving servers, which are written in Java. And their SLAs are very, very important to them. Then they get enriched, and eventually they're being sent into a Kafka. Now, it's very important to mention, it's very important to remember that this layer, everything that's concerned with data serving and collecting the data is regional. So at the time of these architecture, we had several data centers across the world that were collecting that data. So everything you see in the front-end layer is being replicated across these data centers. And so the data is being sent into the data center's Kafka. So for each data center, we had its own Kafka. From there on, the data goes to our one main central Kafka on AWS, the data processing layer. And so the data gets replicated from Kafka, from the data center Kafka, and into the AWS Kafka using uReplicator. From there, we have some pretty big Spark streaming processing applications that we personally call the data loaders. They read all the data from the AWS Kafka and they spill it on into S3, which we call RDR. So RDR just stands for raw data repository. And that's just our data lake sitting there in S3. From there on, we have the data processors, which are Spark, Bad Jobs. They read all the data from RDR. They write it into several data stores. Each data store is serving an entirely different application, entirely different need. So we've got Druid there, Postgres, MySQL, and again, RDR. So some of these enrichments and aggregations are being written back into S3, back into our data lake. And then eventually we have that another Hive layer. So the applications and the application query and analysis layer, they can read the data from each one of these data sources, but they can also reach the data altogether through Hive. Next slide. And so our architecture really had little fires everywhere. And what we're going to do now is we're simply going to cover all of these little fires so that you'll really understand the need for a data auditing system. Next slide. So let's start with the data arrival pain points. And if we'll first just zoom in into that connection between the data serving, right, between the backend and the data layer. As I mentioned before, we had several Kafkas, right? We have a Kafka in each data center, and the data is being replicated in a Kafka AWS. What could go wrong? Well, first, let's start with the uReplicator. If you're not familiar with the uReplicator, it's a project made by Uber. It's based off of Kafka's own mirror maker, and it's simply supposed to replicate data. So it replicates data from the Kafka data center into Kafka into AWS. What could go wrong? Well, aside from just, the uReplicator crashing and then data not arriving, there are some problems that are actually worse. And the main one is because of the way the uReplicator and the first version was implemented, is that sometimes it gets stuck on a few partitions. So what do I mean by that? Let's say that you have a topic with 500 or 1,000 or 1,500 partitions. So it's a pretty big topic, right? And we're talking about more than 50 terabytes of data flowing into our systems daily. Let's say that the uReplicator is up and running and you don't get any alerts, right? So everything seems to work completely fine. But apparently, it's not replicating some 10 or 50 or 100 out of the entire topic's partition. That turns into a really big problem, right? Because without knowing, not all the parts of your data are actually arriving. Not all of your data is actually being replicated from that regional Kafka and into the AWS Kafka. So that was a really big pain point for us. Next slide. Another data arrival pain point would be what happens after the Kafka AWS. So what happens after is, as I've already said, we had some pretty big data loaders, right? Spark streaming jobs. They would read all that data from Kafka and then spill it into RDR. And what can go wrong here with data arrival? Well, let's start from the one big Kafka, right? So some of the brokers are crashing, and then you have arrival latency on that data. Same goes for the Spark applications. They're crashing, the alerts start popping up. Someone has to go and look at the Spark application, see what happened, right? And then again, your data gets delayed. Next slide. And so these were our pain points, right? But then what didn't mention? I didn't actually mention how we recovered from these failures. Next slide. And so if you think back, right, I said that the uReplicator got stuck or the uReplicator crashed. So what would we do in this case, right? We'll just restart the uReplicator. We'll just start the replication again. And from that point onwards, we'd say, okay, we're totally fine. It's replicating again, so this has to be fine. Next slide. And the same goes for the other part of the pipeline, right? So some of the brokers in Kafka crashed or the Spark streaming jobs crashed, and we'd say, okay, we started them back up again. We solved the bug. We fixed it. But we didn't really know when the entire of the late data has actually arrived. We really didn't know if we had some data missing or if we had some data duplicated, because we didn't really know when did our data actually arrive at each and every point of this waterfall. Next slide. And so these are the problems that we had with data integrity. And data integrity is very, very important to us. And another thing that we have to mention, and now I really want to go into that question, is at the end of the day it and why it is actually important. So it's important primarily because in our world, in the media world at Nielsen, what we want to do is we want to aggregate daily data. We want to aggregate an entire day of data, because we count users uniquely per day. So to run your processors, to run your data processors at optimum, you have to run them only when the entire day's data had arrived. So if I'm running my Spark application at 2 a.m. or 3 a.m. and my entire data did not arrive yet, I'll just have to run that process again, which will cost me quite a lot of money. So the end of the day question is actually just the question of, did all of my data has actually arrived? Can I run my processor now? Next slide. And so we tried solving that question at first using a fixed time, right? We use Apache Airflow for scheduler. And so we said, okay, let's do a fixed time solution. So what does that actually mean? We'd say, okay, so let's say the entire days of data had arrived at 10 a.m. Okay, so let's just set our processing application at 10 a.m. And then suddenly we had a problem, right? Something crashed, data had arrived quite late, and then at 11 a.m. it wasn't really a good time anymore. So we had to manually, again, rerun the processing job. Okay, great. We said, okay, fine. So a fixed time solution is not a good enough solution. What can we do instead? So we said, okay, let's do AWS S3LS, right? So what would happen is that we'd get the time that our files got written at. And we'd say, if 2 hours had passed and no new data has arrived, then that means that it is the end of the day. And yeah, we were wrong. So let's say that something crashed, your data loaders have crashed, your view replicator has stopped working, so no new data is actually arriving. And it's not arriving for some time now. Let's say it's not arriving for more than 2 hours. What would happen is that our processing jobs would again start processing an entire day of data, but it wasn't actually the end of the day yet. So these solutions were just not good enough. Next slide. And if we look at it at the context of this architecture again, you'll see what I mean. So the data loaders have crashed, some brokers in Kafka has crashed, or our entire Kafka in AWS is not available anymore. Data is arriving late into RDR. The data processors are not aware. They're already processing data, storing it back in RDR, Postgres, Druid, and then next slide, our Diana, next slide. Okay, cool. And then our applications, they're also querying that data, right? The reports, data science, billing, some of them are actually producing their own data sets based upon that data. And so not only the data processors have to run again, but all of these applications have to redo their work, right? Again, costing a lot of money in order to get an entire day of data. Next slide. And so if we go back to our entire architecture, you can really see that we had a lot of little fires everywhere. But what's even worse is that we were just not aware. We didn't have that information in regards to our data. Next slide. And so for all of these reasons, right, data arrival pain points, and for being able to answer that question, is it the end of the day yet? We decided to design our auditing system. So now what we'll do is really go and delve deep into that design and what is the data that we're actually dealing with when we're talking about auditing data. And I have some points that I really want you guys to keep in mind. So what should we keep in mind? The first thing would be is that we don't have one Kafka topic. We have several of them. And that number is not fixed. So if there's a new project, there might be a new type of data. There might be a new Kafka topic. The second point are some points about our data serving infrastructure. And I've mentioned them actually before. So I said SLAs are very important to them. Another thing is that they're written in Java, and each and every server in the data serving infrastructure is actually running 2 JVMs. So there are 2 processors running the data serving servers on the servers. And each one of these JVMs is working against several topics. Another thing is that they're using our own Nielsen Kafka producer. So it's a Kafka producer, but with some extra layers. And so we decided to implement this auditing subsystem right on the Kafka producer. And because of the SLA, our code had to be really, really optimized, right? Cool. Another point that I want you to keep in mind is the fact that we use Avro. We use Avro data format in all of our topics for all of our data. And this had actually made the solution a lot more easier. Okay, so when I'm talking about auditing window, why is the word window written on this slide? Why is it here? Next slide. So auditing window is our metadata object. And I think that if you'll take all the points I just told you to keep in mind, you'll see why all these data points are actually here in this slide. So you can see the key for our auditing window would be topic, server, process, and audit time. So the first 3 are pretty simple, right? We're keeping track, we're auditing for every topic, for every server, and for every process running on that server. What is auditing time? Well, you can't really audit forever, right? So you're looking at a certain scope of time. You're thinking how much data, how many events were shipped during a certain scope of time out of the server and into the regional Kafka. So auditing time is that time scope, right? And auditing window is that object. So for every auditing time, we're keeping track for that window. For every topic, for every server, for every process, we're keeping our value, which is the counter. How many events were actually shipped out of the server into that regional Kafka? And so what you can see on the screen before you is just that Avro definition. So it's everything I've just said, but in Avro format. Next slide. So the moment you've got that object, right, you know for every process on every server against every topic, you know how much data they actually produced, you know the exact number. But in order for us to actually have that auditing information on the other side, we have to connect it to our data. And so what we created is the auditing header. And this header we actually injected, and we'll go a bit more into how in a few slides. But we just injected this piece of data into every message of every topic that we wanted audited. So what this has is a window timestamp, a server name, and a sequence ID. And the sequence ID is a bit of a spoiler. We'll go into that in the add-ons. So let's just address the first 2. And the first 2 are very simple, right? So server name has a server name and the process ID together. And the window timestamp is, again, that time scope that we're referring to in our auditing window. So later on, when we'll see how our output data actually looks like, you'll see how this auditing header connects us with the auditing window. So now we'll be able to count. We already have the counter telling us how much data, how many events were produced by that process running on that server. And having the auditing header, we'll be able to count how much data actually arrived to the other side, into the RDR. Next slide. And so if we actually just look at an entire record, and you can see I anonymized some fields. This record is of type raw event data, right? And so it has its own header, which is a different object, and it has a user create timestamp and some other fields. And up in the second row, it has the audit header. So we just added that audit header to every Avro definition of every topic that we had. Next slide. So what you see before you right now is just our Java code that we implemented in order to actually inject that data into our message. So how did we do that? So this code runs as part of our producer, meaning that this code runs for every Avro message, no matter what is the message. So the way we do it is we take that generic record, we get its schema, we get the location of our audit header object, and the minute we have that location, we can actually just run it over with the data structure that we created in our code. So using this very simple bit of code, we were able to just put this auditing header information into all of our data. Next slide, please. So back in context to the architecture we looked at, you can see that everything we talked about just happens in that data serving queue. So data serving collects the data, and the moment it actually uses a producer to ship it onto Kafka, the data gets injected with the auditing header. And then in the meanwhile, we have a process running on the data serving server as part of our producer, creating data auditing window objects. It counts the data that's being sent out, and then it sends out that same object on next to Kafka. Next slide. So I've just said we're just sending it like onwards to Kafka, and I'm not sure, but if anyone had noticed the logical problem here, and the logical problem would be is that we're trying to audit the data that we're sending through Kafka using Kafka. And that's a pretty big issue, right? Because if we actually have a problem with replication, or if we actually have a problem with Kafka, that simply means that we're not going to get the audit headers, that's true, but we're not going to get the audit windows to collect either. And so we've implemented another solution after we've noticed this little bit of a problem. So we've just created a simple solution using Amazon API Gateway, right? It's an Amazon service that really helps you create REST services really simple. So we used Amazon API Gateway. We wrote a really simple Lambda in Scala that gets that message, gets that object, the audit window object that we've just discussed, parses it, and ships it onto our data store. But since we've implemented the Kafka topic solution first, we just decided to keep both. Why? The reason is very simple. A, because it already existed, and B, because we actually discovered it's really nice. We can actually see if there's a problem with a gateway or if there's a problem with Kafka. But we just decided to keep both. Next slide, please. So again, in context, we said that the data serving is everything we discussed happens at the data serving layer. So data serving consumes the data, produces it into the regional Kafka, and again, it gets replicated to Kafka and together with all our audit header objects and the audit window objects, which are our metadata. They're getting produced from data serving into Kafka, but they're also getting produced from data serving into our Amazon API Gateway. Next slide, please. Cool. So how do we actually consume our auditing data? So we've just discussed how we actually consume the audit window. So we do it both ways. We do it using a Kafka consumer since it goes through Kafka. We also do it straight through API using our Lambda. Now, the auditing header right now is already part of our data. So it's getting read, it's getting consumed by the data loaders from Kafka, and then they write all that data into RDR. So we wrote some of our own Spark job consumers consuming the data from S3 from RDR, consuming only the audit header. It aggregates them, and then it ships it into our data store. We've implemented this solution using EMR, right? Elastic MapReduce service by Amazon. So you can run several applications in parallel. And so all of our auditing consumers, both the Spark Kafka consumer and the S3 consumers, so all run on the same EMR. Next slide. So again, in context, you can see that the data audit window consumer right there and the data audit header consumer, they all consume the data, the auditing data, and they eventually write it into the data audit table, which we'll discuss right now. Next slide. Okay. So storing our data. I don't know if you've noticed, but auditing data is pretty structured. We have a key and we have a value. And so we decided to store our data in Postgres using the Amazon RDS service. Next slide. So when we decided our output table, we came to the conclusion that we first need to understand what are the questions that we want answered using that data. So the first would be, what are the levels of granularity? So we have topic, right? We have topic, we have server, we have process ID. These are the obvious ones. Which ones are not the obvious ones? So one would be region, right? So as I've said, we had our data serving our front-end infrastructure. It's regional, right? So if we have a problem with your replicator, the best way to know would be using a regional granularity. The next two questions would be arrival rate and arrival latency. So arrival rate is just how much of the data that was produced for a certain time scope actually ended up arriving. So that was pretty straightforward. But the next question is a bit less trivial. So it's arrival latency. And arrival latency just means how much of the data that was produced actually arrived within 1 hour, or within 3 hours, or within 5 hours. Next slide. So if you look at our table, you can see how we answer these questions. So again, we have the obvious columns, right? We have the auditing timestamp, which is what is this time that the auditing window started for. We have topic, server, and process. Then we have event count, which is what is actually the number of events that was counted. Location. So the location column is here because we decided to store all of our data, both the auditing windows and the auditing headers, in one Postgres table. So the way that we differentiate between what is the actual data source, is it the metadata or the data itself, is using the location column. And so the add-ons are region. I've told you that regional granularity is important to us to know if there was an actual problem, for example, with a U replicator. So we started extracting the region column out of the server name. And the second column is insert time. So insert time is just the actual time that the data arrived into the auditing table. And so if you just deduct the auditing timestamp from insert time, you actually get the latency, right? You actually get the time that it took the data to arrive from the moment it was produced to the regional Kafka and on until our Postgres table. Next slide. And here you see an anonymized example of our data. So topic 1, topic 2, and topic 3, it's what we're playing with today. You can see the region that it's being really just extracted out of the server name. If you'll just look at location for a moment, you can see that we have Kafka windows and RDR headers. The reason for that is the first part is an indicator as to where we consume the data from. And then the second part is, what is this type of data? Is it the metadata, meaning windows, or is it the actual data? So that's headers. If you look at insert time and window timestamp, they're both in UTC. So that's really important for us because we work cross-region. Our developers at Nielsen's NMC, we sit in Israel. So working in UTC was really, really important for us. And the last column that I really want you to pay attention to is the event count. So some of the values in event count are straightforward. You can see a really high event count for some Kafka windows. But what's really important to mention, what's really important to notice is that some of the event counts values, they have zeros. How is that possible? Well, if you really take a look, you'll see that the event counts that have zeros, their location is in Kafka windows. So the reason why they have an event count of 0 is very, very simple. The way we designed the element that actually creates these auditing windows on our producer side is that for every 5-minute interval, for every auditing window timestamp interval, it starts that count again, right? Because we said that we're auditing for a certain scope. And so on startup, the consumer receives a list of topics to audit, but it doesn't actually mean that the server is working against these topics. So sometimes we'd create an auditing object, but the server would not produce any messages onto the topic. So you'd get a count of 0. So a lot of the times that's perfectly fine. Not all servers are producing to all topics at given times, but sometimes this can actually detect a problem. But I think it's a really interesting component to just notice. Next slide. Okay, so what you see before you right now is the logo for Apache Superset, and that's a BI tool that that we're using, and that's a BI tool that we decided to use for the auditing data. Next slide. So the first thing that we'll see is just data arrival within 3 hours in the last month. So that's really our arrival latency for this topic. And I think that you can notice that we have a bit more than a 100, right? It's 100.220. And the answer is yes. Yes, we had some data duplication. And we are aware that in the big data world, some data duplication, some data loss, that's acceptable. We're dealing with large amounts of data. But when you see these numbers going above 120 or above 160 or above 200, you know that you have a problem. Next slide. And so this is just arrival rate. So arrival rate for the last hour, arrival rate for the last 24 hours. Next slide. And what you see now is just the SQL that we actually provided Superset with in order to create most of these charts. So you see that we use the location in order to just create that producer count and RDR count. And we use these values in order to do all the calculations for arrival rate, for arrival latency, and just the grouping by factor is the one that's providing us with the granularity. So in this case, it's just the topic name. Next slide. So what you see before you now is, again, the logo for Apache Superset, but it's also the logo that Apache Superset used when it's just loading data. So you created your chart, right? You created your BI chart, and you're waiting, and you're waiting, and you're waiting, and all you see is Superset's logo. Next slide. And so what I want to do now is just give a little shout out to my dad. My dad has been a DBA and a programmer for 30 years more than me. And I'm doing this shout out to my dad because when I came to my dad with a query that was running on the table for 1 minute and 15 seconds, he didn't give up. And he made it run for less than 15 seconds, which was pretty much amazing and really, really helped us. So thanks, Dad. Next slide. So how did we do it? How did me and my dad do the optimization for PostgreSQL for our auditing data? So the first thing we did is just weekly partition the data. So if you think about auditing data and log data, users don't actually look like at data that's like 2 months or 3 months or 6 months old, right? We're usually interested in the one that's like 1 or 2 weeks old. We did weekly partitioning, and we decided to keep 1 month's worth of data in hot storage. The second thing we did is also pretty obvious, so that would be indexing, right? We created our unique index on our key. I've already said the unique index, so that would be, again, the window, the server, the topic, right? And then we also created some complementary indexes. So we looked, of course, at the queries that are being ran quite often. We looked at their predicates, and we used them to create some complementary indexes. Another thing is if you're using Postgres on RDS and your queries are not running quite as fast as you expect, I really encourage you to look at the 3 factors that are on my screen right now. So the max worker processors, the max parallel workers, and the max parallel workers per gather. These are the 3 variables, 3 configuration options that will really boost up the use, like the way that Postgres runs queries in parallel. And you'll be surprised at what it can do to your queries when they use 10 workers instead of 2. And last but not least is, of course, tweaking the optimizer. So I know that we all think that the optimizer for the database that we use is the best, and we'll just give it any query and it'll do its magic. But sometimes tricking the optimizer and just doing the exact opposite is apparently the best thing to do. And a quick, really quick example is if you're using in as a predicate and it has some strings inside, let's say 3, it has 3 values inside. So Postgres' optimizer would actually do better if you just do 3 selects with an equal predicate instead and just use a union in between them. The optimizer would actually just perform better using that later query with a union. Next slide. I mentioned weekly partitioning, and of course, there are a lot of databases today, like relational databases, where you partition your table, and if data arrives and the data arrives and it has a value for a partition that doesn't exist yet, that database will just create that partition or use a default partition. So if you're answering yourself if that exists in Postgres 11, next slide, it doesn't. Next slide. So what we actually decided to do is just do the whole management of partitions using Apache Airflow again. I don't remember if I mentioned, but it's the product that we use for scheduling, right? So we just created a simple process that would create these weekly partitions, again, on a weekly basis. So what I've decided to share with you is the 2 basic queries that we've used to create that process. The rest of it is not really interesting because what we do is just we play with dates, increment them by a week, and then create the partition. So by using just some standard names for our partitions, partition prefix, and then the date for that partition, we were able to create a very simple process that runs every week, selects the last partition with the max date that was created, and then advances it by a week. Next slide. Another thing we did was offloading data to history. So I've told you before that we partitioned the table weekly, and also we've said, okay, users that look at log data and auditing data, they don't really look at more than a month's worth of data, right? But we didn't really want to throw that data away. So we've created a process that, again, would run weekly. After it will be responsible for offloading those partitions, those old partitions. So we've just created a Spark job that reads that old information, aggregates it, collects some cool statistics that we thought might be useful in the future regarding data arrival latency and arrival rates, and just pushes it into a different table that we can think of what to do with later on. Next slide. So finally, we can go back to that question, the question of, is it the end of the day yet? And if we'll think about the data that we've collected, right, and the fact that we can already calculate arrival rates, we'll understand that we can now maybe answer that question, right? So I'll just remind you guys, so the question, is it the end of the day yet? That's just an acronym. That just means, did the entire days of data arrive? Is yesterday over yet? Is all of our data in? So in order to answer that question, based off the data we've collected, we've again used Amazon API Gateway and a Lambda function. And that Lambda function would be able to answer all your questions regarding the end of the day, by topic, by region, by time spec, right, for a certain hour, for a certain day. We'll be able to give you that answer. You would ask for a certain topic, and it would say, yes, it's the end of the day. Next slide. So what do we need to check in order to answer that question? And what you see before you now is the simple pseudocode for the logic of that Lambda. It starts from checking the validity of the input parameters. But I'm just kidding. Next slide. I just written the 3 main questions for you. Diana, next slide. Yes, okay. So is it the end of the day yet? We have to answer 3 questions. First would be, is the data arrival rate for the entire scope high enough? I mean, if we want an arrival rate of more than 99% and it's 95, then no, it's not the end of the day yet. The second question is the number of audit windows that arrived for that entire scope. So if we're looking at yesterday and we're thinking, is it the end of the day yet? How many windows actually arrived? We have a certain number of servers. They have a certain number of processors. They're working against a certain number of topics. We know how many windows are supposed to arrive for a certain time scope. And if we don't see that number of windows, if we don't see that number of events in the table, that we know that we have a problem with our auditing subsystem, and we can't really answer this question. We can't really know if the day is over. And the third question will bring us back to the arrival rate, to the one that was higher than 100. So I've written here the arrival rate for the last window. The last window is 11:55 p.m. And the question is why? Why do we need to know what's the arrival rate for that last window if the data arrival rate for the entire scope is high enough? And the answer is pretty simple. So you saw that sometimes we can get arrival rates that are higher than 100. So let's say we had a really high arrival rate, like at 2 p.m., we had an arrival rate of 200 or of 300. The minute we try to calculate an arrival rate for the entire day, we'll get a skew, right, for that calculation. And so we said, okay, that's fine by us. But because of that reason, we need another guarantee that the day is actually over. And that's why we decided to just calculate the arrival rate for that very last window. So we said to answer, is it the end of the day yet? We'll just look at, finally, we'll just look at 11:55 p.m. and we'll see if the entire data of 11:55 p.m. actually arrived. And if it did, we'll say, yes, it is the end of the day now. Next slide. Okay, we're almost at the end. I hope everyone's holding up. So just some alerts and add-ons. The first would be alerts that I've just mentioned. So we created alerts using different levels, different factors of granularity. We created alerts on regions or on topics and on servers. And this really, really helped us pinpoint a lot of the problems we were having. Because if you have an alert on a specific region, this can be a problem with the data loaders. This has to be a problem with the replicators. And if you have a problem with a certain topic, then you know that it's probably a problem with your data loaders and not with your replicators. So this really, really helped us pinpoint problems and save a lot of time. The second would be detecting duplications. I don't know how many of you remember, but when we looked at the Avro definition for the auditing header, we saw that there was an element there called sequence ID. And I said, it's a spoiler alert because it's an add-on. Well, it is an add-on. Why did we create sequence ID and what it actually is? So when we started noticing arrival rates that are higher than 100, we said, wait, this is really weird. What if it's a problem with our auditing subsystem? So what we did was actually just add a sequence ID. So for every window, we're counting events. We're counting that in the auditing metadata object, right, in the auditing window. And in the auditing header, we're adding a sequence ID. What is the sequence ID of that message in that window? And so if you want to detect duplications, you can just consume your data from S3, from our RDR data lake repository, group by the auditing key and the sequence ID, and see which ones of your groups have more than one event in. And yeah, we discovered some duplications using exactly this method. And the final add-on is more like looking into the future. So the reason why we use that column name location was to really differentiate between the data, between the metadata and our actual data. But we also thought about the future. We said we might want to add more consumers at different points of our architecture. So that's still an add-on, that's still in the future. Next slide. So these are just some snapshots of our alerts. So our alerts are popping in Slack, and you can really see there was an abnormal write for a few regions of 0 into Kafka. And you can probably say that if there are all regions are with 0 arrival rate, the problem is probably not with the replicator. And then in the second picture, you can see that for topic deliver and for topic read, the arrival rates were 78 and 67. So our alerts look like pretty much like that. They're really, really helpful. Next slide. So this is actually Diana, next slide. So thank you. Diana? Okay. Do you have any questions? Because this is pretty much the end of my presentation. Right. So regarding the schema changes, we don't use Kafka Confluent. We don't use Apache Atlas. That's a really, really good question. So I don't know if you guys are looking at the chat. The question, I'll just reread the question. The question is why you don't use Apache Atlas or Kafka Confluent with really good possibility to detect schema change and use this hook to make further automation. Great question. We manage our Kafka by ourselves on EC2 servers. The reason is the historical server, historical reason, sorry. We're looking, like, right before I left Nielsen, we were really looking at our Kafka's architecture, and we were really thinking in a few directions of how to implement it differently. So that's a really good question. The reason is just for historical reasons. And to detect schema changes, we're actually just use schema registry. Any more questions? I'll also be available later on in Discord, and you can always approach me on LinkedIn or any other platform.